what Chapter 4 has to offer. It's actually one of my favorite chapters. For one thing, it fits in the holiday season because it tends to not be as hard as what we've been doing. A little bit of a breather. A lot more, there's to some degree a lot more skills, but you can finally now start working with a concept that kind of like with when in Algebra 1 where you got stopped with your complex solutions and now you have a way of dealing with this. Chapter 4, same thing. If you had, let's just take something pretty easy to understand. 2 to the x, right? If I said 2 to the x is equal to 4, and I said, well, 2 to the x is equal to 8. You would know what x is, right? Because you know something, 2 to some power is equal to that, correct? Okay, so what would this be? Well, x would equal what? If I was to solve this equation, x would equal 2. If I was to solve this equation, x would equal 3. Okay. But what if I wanted 2 to the x is equal to 6? You have no way of dealing with that, right? Well, we're going to undo these with logarithms. In order to get comfortable with the logarithms, we have to be very, very comfortable with the exponentials. So 4.1 and 4.2 are going to focus entirely on exponential equations. And then we're going to head into logarithms, which are actually kind of fun. Okay, so the first idea is that with the difference between a power function and an exponential function is where the variable is, okay? So these are going to grow very differently, okay? If you were to, I would encourage you, like in, say, Desmos, at some point in time, you could just kind of compare how they grow, right? In other words, if I do 3 to the x or 4 to the x. But all we're saying is we've got a base, and what we don't know is what we're raising it to. The most common application of this is time. So if you had algebra with me, at least, most algebra classes will do at least a little bit of exponential functions where you might say take a population that grows, right? And it'll be growing as a function of time. So let's take something that most of you would have some kind of an idea about. And I think I'm going to have you pull out SB page 21. This is an activity that would have been towards the beginning of your notebooks. They have it in chapter 1. It makes a lot more sense than when you pull it out about now. What it is an exploration of something that grows at an exponential rate. So I did not know this was a thing, but there is something called water bears. Okay, they're some kind of microscopic organism that apparently when you look at them under the microscope, they look something like a bear and they grow in the water. Okay, so they have a growth rate, right? Like they're microscopic organisms like bacteria do or algae or anything like that. They have a growth rate. One, how much of that population do we start with? And then secondly, what is its base, right? Sometimes we might think of doubling or tripling or something along those lines, okay? So before we get going, we're going to use, they've given you this little expression because it's going to kind of be working backwards here. And they've asked you to simplify this. What would this simplify to?
Cancel the B.
The b's would cancel. Easy to see that. Okay. So I would get a to the n plus 1 over a to the n. Put a number. Okay. Let's just say I have a to the 5th over a to the 4th. What would happen?
Just A.
It's just a. Right? Do you guys see that? You put a number in it. Makes it really clear. Any time that this is just one more than this is going to cancel all but one of them. All right? Right? Okay. So this is actually going to turn out to be a way to recognize if we have an exponential function. If you have a table of data, right? If you divide, if you get a constant, every time, that's going to be the base of the exponential function. So far, if you've seen a table, like if you look at, we have different ways of figuring out what kind of a function we have. If I have a table of data and it's growing at a constant rate, right? That every time y goes up 1, x goes up 3, right? If I have a slope of 1/3, right? I have a constant rate of growth. That would be a linear function. If the first differences are the same, it's linear. If the second differences are the same, it's quadratic, right? We have different ways of recognizing it. Turns out that this is how you could recognize from a table of data whether something is an exponential function or not. And in fact, you have the ability to do this. We did a linear regression activity earlier this year. Do you guys remember? Where you put in data and you could plot it. It was close to a line, and the calculator could figure out what that linear function is. You have the ability to do that with exponential functions as well, okay? So take a look at, I was going to go to number 3. We should do number 2. We'll do number 2. This is number 2. If a to the 5th is equal to 12, how would we find a? How would we solve for a? We take the fifth root. Make sure you can do that on your calculator. I'd like to see that everybody can do that. You will need to use that skill. All right. So if you're using a graphing calculator, what you would do is you would put in the 5, okay? Then use the math key and find the x root. If you hit enter, it's going to give you the 5th root, right? Okay, and then you would enter in your 12, and you would get approximately 1.64375 ... right? It's going to be an irrational number. Everybody can do that? Okay, all right? Okay, going to number 3. If you saw, notice, so if this was a table of data, up until now you might have said, hey, is there some kind of a power function here? It's obviously growing, not at a constant rate, right? If you go from 120 to 360, you've added 240, right? But going from 360 to 1080, you're not adding 240. So it's growing pretty fast. So the way you would test it for whether or not it would be an exponential function is you would take a term and divide by the previous term. What do you get? If I take 360 and I divide by 120, what do I get? 3. If I do it the next time, if I take 1080, divide by 360, what do I get? 3. It's basically 36 divided by 1080. You can use a calculator. And obviously these numbers are pretty big. In fact, go to 10. If I took that 2,461,960 divide by my 787,320, well, it's approximately 24 divided by 8. It should be approximately 3, right? Yeah, exactly 3, because of the 120. But the point of it is that you basically have something that is tripling over the time frame, right? So the base, or the a, is going to be 3, and that's how we would determine that, okay? So with every exponential function, I'm actually going to say this, I'm going to call this my water bear function, okay? The number of water bears is going to be determined by a time increment, which I think in this case is days, right? The number of days, right? Okay. Now, what's the growth rate? It triples, it's 3, base of 3. It triples every t days, right? Okay. But notice that if on day 1, I don't just have 3, right, of these bacteria. What did I start with? I had to start with something. Huh? Well, wait a minute. So on day 1, so let's look at this, okay? So I've got a to the t, right? On day 1, if t is 1, I get 120. I know that a is 3. What did I have to multiply 3 by to get to 120?
40.
What does that 40 represent?
The water bears in zero.
the number of water bears I started with. So you understand that if you're going to grow something in a lab, right, you have to have something to start with, okay? So, and typically you can't, well, I guess maybe you can start with a bacteria. If they split, right? Now if it's rabbits, you're going to need 2, right? Okay? But you've got something that you start with, okay? So when we talk about this form, capital B, A to the T, okay? The B is the start, I would think of it like a seed, right? What are you going to start your sample with? That's what we start with, okay? So I know that I have 3 to the T, and I started with 40, okay? So that's my function, okay? It's not, and notice PEMDAS would say exponents first, then multiply. So it's not multiply and then take the exponent. So the parentheses are usually thrown in there to make sure people don't do that, right? It's not 40 times 3 to the T. It's 40 times 3 to the T, okay? All right. So we've just found, this is number 3. We found what A is, it's 3. We found what B is by plugging in. And then take a look at number 4. Real life is not going to be this clean, right? There's no way this is going to happen. In biology, things are messy. We get variation in biology. Okay, so we're not going to get an exact of 3. If you were to estimate what the actual growth rate is and the actual B is, just kind of take a moment with your calculators, come up with what you would estimate it to be. It's not going to be exactly 3 or 40. Okay, let's see. Let's go to, so if you're going to enter in data, you want to go to stat. You would hit stat and then just hit enter because you're going to edit. I would probably hit second function memory and clear everything out. So this is a nice thing to know how to do. Hit second function memory and then go clear all your lists. That way if you have data in there that you just don't, you want to start with a nice clean slate, you could hit clear everything in the memory. And now when I go to edit, I'll have nothing in there. I'll just start clean. All right, so I'm going to go ahead and do that. I'm going to hit, so I hit stat again, and I hit enter to edit, and now I'm just going to enter in. List 1 is going to be 1 through 10, right? So you can hit 1, 2, 3, 4, hit enter, and it just keeps going down. Make a mistake. I should have 10 items, so...
Mistakes help you learn.
Huh?
Mistakes help you learn.
Takes up what?
Mistakes help you learn.
Yeah, actually, what's it? Exactly. There is a function, I just haven't used it for a long time, that will allow, if you, let's just say you have a lot of things to enter, but typically by then we're going to use some kind of a data import function. However, there is a list filler you could find if you look it up on how to do it on the TI. But now I'm going to enter in the population data that they gave me. Just be careful. I'm using the mouse. So, okay, you can look at the data and table, but what I really want to know is you don't have a function yet, right? So table is just going to do whatever functions in your y equals. What I want is I want the function. Pretty good. We'll find out in a minute. Okay, so so here's the thing. If I was a biologist, right, doing this, I know this is the type of a population that's going to grow at some exponential rate. So I'm going to expect, it's not going to be linear, it's not going to be quadratic. I'm going to expect it to be exponential growth. So if I want to know kind of what that averaging is, I'm going to use the exponential regression function. Okay, under stat, if you look under tests, okay, so when you hit the stat key statistics, it's going to default to edit. Go over to calc. Do you see that menu? And then go down until you find exponential regression right there. So if you notice, linear regression is if we think it's a line. Quadratic, cubic, you can see you've got other options here. That's another linear regression. This is logarithmic regression. If you think you've got logarithmic growth, we're going to use the exponential. We think this is growing exponentially, so we're going to hit enter. Okay? X list, that's my X data is in list 1, my Y data is in list 2, so I'm going to leave it that way. If I did it in different lists or in different order, I would change those, right? But typically that's what I do. There is no frequency list in here. You'll know what that is if you do a stat class. I do want to store my function into my Y equals, so I'm going to use that function. Going to my vars, you hit vars, and then you go over to Y vars, and you hit function. So what I did is I hit this is for variables, right? And I went over to the Y variables. I'm going to hit 1 for function. I'm going to hit enter, and I don't care what I had in Y1. I'm going to allow it to overwrite it. I'm going to hit enter for Y1, and now it's going to put it in there, and I'm going to hit calculate. Okay. Hit enter. And there it is. That's my linear function. So notice, do you guys see? Okay, in statistics, they will switch variables from what you see in a pre-calc book. Their A is the B, and their B is our A. Okay, so they actually switched it. This is what they have. This is a statistical operation. B stands for the base, which actually makes more sense to me. What is the growth rate, guys? Actual growth rate of the water bears. Take a look at the data. About, that's going to be, the base is about 2.5. Okay, so they're growing by about 2.5 times every day. Okay, not 2, not 3. And we started with about, based on this data, we would have started with about 38 of these water bears. That's what that means. If you want to go over to your Y equals, we did store it there. Okay, notice. And if I want to see it, Desmos, but here, I'm going to go here. I'm going to go to my window. I'm going to make my X-min 0. 40 days, let's see what we have in. It's going to grow really fast. Let's go with 10 days. So there's my X view of my function, and I get a much better picture, right? Okay. And that's how exponential growth happens, right? If there's nothing to dampen the growth, if there's no predators, there's no disease, there's no lack of food, things will just continue to grow without any other limiters, right? You'll need to remember your exponent rules, okay? All right? Because if you notice, x is going to be in the exponent. So everything that we know about exponent rules is going to end up applying here, okay? So let's think about, I'm going to just go ahead and use the 2 to the x. Right? Okay. So if you think about it, 2 to the 1, 2 to the 2, 2 to the 3, ... Right? We have that kind of growth. This is going to be 2, 4, 8, ... Do you guys notice we said that to determine whether something grows exponentially, you're going to take the latest term and divide by the previous one. 8 divided by 4 is 2. 4 divided by 2 is 2. 2 divided by 2 is 1, which is what justifies that rule, right? Okay. And then we go down to, if we're thinking about our negative exponents, again, thinking about this as a number line, right? Our exponents are kind of like the number line. Again, think about this. It's 1 divided by 2, right? And if I take 1/2, dividing by 2 means, yep, there we go. And what we're really saying is, we already know the negative exponent doesn't mean negative number, it means take the reciprocal, okay? So, if you notice that this is the pattern, what do you notice about the domain and range of the exponential function? First of all, think about the range. What can come out of an exponential function? Huh?
It's greater than 0.
Yeah, I cannot get 0, and I cannot get a negative number. Does everybody see that? It's not going to be possible. So if you remember with the square root functions, sorry about that, remember with square root functions we limited, right, our domain in order to have a function. Notice with exponential functions, we have pardon?
It's just not possible.
Yeah.
After that.
We have something along the lines of that, right? Okay? But we can't get negative values. All right? Pardon?
Unless there's a negative.
Unless there's the function itself. B can be negative, or whatever the coefficient can be negative. I'm trying to think where that would apply. It would, there's applications for it. I can't think of any at the moment, but, so, you're going to need to remember your exponent rules for this chapter. We've worked a lot with those. So hopefully they will be coming into play. Let's think about a graph, okay, of what this is going to look like, all right? We're going to think about what happens if A is greater than 1, A being the base. Okay. What happens if A is less than 1? And of course, what happens if A is 0? Or if X is 0, whereas no matter what the base is, we know that we're going to have an intersection of 1. They're all going to intersect at 1. What's going to happen over to this side, though, is how quickly it will grow, right? If the base is 2, it'll grow at a certain curve. If it's 3, it'll stretch it up. It'll grow faster. If it's 4, and so on, okay? So let's take, so again, I guess if I put in a 1, let's think about this. This would be my fraction. And you can see why I'm going to get something that's going to look like that, right? When we graph these, okay? So it's just going to be determining whatever A is going to determine how steep and how quickly it grows, right? Okay? So chapter 4 starts on page 302. There's some nice little notes here about what A can be, okay? What A can be. Can A ever be 0? Just let's think about this for a moment here. Could A be 0?
No.
What would happen if A was 0?
The point 0 would not pull the other function.
What would 0 to any power be? Just 0. We would have a constant function. It would not be an exponential function.
It's definitely X.
There's another number, think about it, that can't be a base.
Oh. No.
What would happen if A was 1?
It would always be 1.
It would be a constant function, okay? So we do have limits. A cannot be 0. A cannot be negative, okay? So A has to be greater than 0, but A cannot equal 1, okay? So we're going to kind of keep that in mind. And just think about what would happen if it was, right? That we would have that. I have a really good example of why it can't be negative. It has to do with the fact that we could end up with 2 possible solutions, therefore it is no longer a function, and it's in complex numbers. I'll pull that out next Thursday. So anyway, those are kind of some of the rules that we have to think about. We did an example 1 is just asking you if you can evaluate that function, right, for those inputs. If I have 3 to the x, I would mention that probably maybe the easier way, if you have lots of different inputs, would be to put it into your graphing calculator as a function. You could use trace, right? You could input and output. But otherwise, you're going to use the function that we just did. If my f of x is 3 to the x, you're going to see function notation almost exclusively in this chapter, right? So if my f of x is equal to 3 to the x, well, if they say, what's the f of pi, what are they asking you to do? They're asking you to raise that to pi, so it should be somewhere in between 27 and 81, right? We would know that, right? Bigger than 3, smaller than 4, okay? So you should be able, that's just a calculator entry. They've actually shown you the calculator strokes there on the top of page 303. If we are graphing, take a look at some other patterns that show up, okay? They've contrasted f of x is 3 to the x, okay? Let me ask you a question. What would, if my g of x was equal to 3 to the negative x, what would that look like? What does that negative x mean? Negative exponents mean? Take the reciprocal, right? So it turns out it's the same as, right, 1 over 3 to the x. Notice that by virtue of the fact that that's a 1, right, it's really the same as 1/3 to the x, okay? So you're going to see that pattern that if I make my exponent negative, right, it's just the same as making my base the reciprocal. I'm taking the reciprocal of the base. And notice, take a look at the difference in the graphs at the bottom of page 303. We don't do lots and lots of sketching graphs. It's more about getting comfortable with what that pattern would be. You do notice they're both going to cross at 1. You do notice that neither one can get down to a 0, but we do get a flip, right? Okay? Because if I have a fraction raised to a power, the bigger the power, the smaller the number, right? Right? Okay, so we're going to see that little pattern there. Number on page 304, again, they've shown you like what happens if you raise up. This should make sense. The bigger the base, the steeper it's going to be, right, as it grows on the other side. And again, same thing with the fractions, right? On the other side, we just get a symmetrical flip. Okay, right? So just kind of like, again, kind of exploring. Take a look at the graphs in the blue box. This is exactly what we just said a minute ago. That 0, 1, unless I shift this, is always going to be a point on my graph, right? Okay. So let's take a look at example 3. This is the kind of thing that we have been working with in other applications, where if we're given a graph and we're given some points that we can work with, we can figure out what the function is, all right? So you take a look at number 1, example 3a rather, okay? We can assume that it is going through the 1, 0. What we're looking for is, we also assume for these that the starting number, the quote big B, remember if we said we were going to do the big B, a to the x? We're saying right now, we're assuming that's a 1. So we're just going to use this. There always has to be a coefficient, but if you don't see it, we're assuming it's a 1. How can I use that point 225 to figure out the base? Well, 225 is an x and a y. Right? What we're solving is, take a look, this is the same as a y. Because we've been using this technique since Algebra 1, plug in to find the missing component, right? If y is 25 and x is 2, what does a have to be? 5. So now we know that our function of x is simply 5 to the x. Okay? Same technique we've been working with before, all right? Take a look at the second one, b. See if you can figure that out without looking at the solution. Same idea. Well, if we're solving for 1/8 is equal to, right, we're saying a to the, oh, I see what you're saying. Yeah, here's, what I would do is I would express this, do you see? So this is 1 over 2 to the third, right? Which is the same as 1/2 to the third, right? Which you're right. We have a tendency, if you're asking for this without the next, we want the x not to be a negative exponent, then we're going to be looking at this as the base. But you are correct that we could this is AKA, we could also say that this is 2 to the -3, right? Or 1/2 to the third, okay?
So it could be 2 to the negative x.
Mm-hmm.
It's 2 to the negative x is the function.
We're solving for a, so we actually found our a is 1/2, right? We were solving for a. Exactly. We only need to find a to get to the exponential function. So the function, this function, would equal, this is the same as 1/2 cubed. Our base has to be 1/2, right?
So it's 1 over 2 to the x or 2 to the negative x.
When they ask for the function, okay, and we're just looking for the a, we don't want the negative version, we just want the base. Believe it or not, they're going to have a preference for the fraction here, okay? It's not that the other one would be, how often have I told you we prefer to not have the negative exponent? It's still going to be the preference. It's not that we don't work with them, but the basic function, we want x by itself. Transformations, guys, there's exactly the same as what we've been doing with every other function. If I know what 2 to the x looks like, well, 1 plus 2 to the x, right? We actually already did this. So if that's 2 to the x, well, and that's a 1, where should 1 plus 2 to the x be? It should be 2 to the x shifted up 1. It's going to be kind of that, just like that, right? Take the graph and shift it up 1. If you look at negative 2 to the x, the negative in front would mean reflect up across the x-axis, where what was positive is going to be, so we're going to look at something, it's going to look like this, right? It's going to be reflected, okay? If I have 2 to the x minus 1, what am I doing to the x? I'm subtracting 1, so that's going to be...
Oh, you're going to move it to the right.
To the right 1 unit, right? So in other words, instead of 0, 1 being a point, 1, 1 will be a point. I'm going to move it sideways, right? So it's going to end up being something, it's going to be moved over to the right. Same thing, same rules you already did in chapters 1 and 2. All right? I'm going to stop right there. That's enough of a soft introduction to get us going.